So can we construct a consciousness meter from TMS-EEG data to an index of consciousness? A highly promising consciousness meter is already proposed. It's a perturbational complexity index, PCI, and it's been already tested on the various levels of consciousness. So going from a previous TMS-EEG experiment, I explained that once we get this EEG response triggered by TMS, we can go from the surface EEG response to the source localized version of the brain response, and then from there we can make some kind of statistical thresholds of the TMS evoked source localized neural activity, and then from there that can be kind of binarized 0, 1, 0, 1, and so on. And then this white part of this figure corresponds to non-significant difference from the baseline before the TMS stimulation. And the black dot point corresponds to the location of the brain and in time that is different from the baseline. That is significantly evoked response. And then when you put it into a sort of two-dimensional kind of matrix by collapsing 3D space into 2D and also over the time, then you can construct this type of the image. And then that can be, that complexity of the pattern can be quantified by some type of the complexity measures. And one particular measure is called the Lempel-Zip compression algorithm. It's basically the same as a zip algorithm that you use to compress your file. If the file pattern is very complex, you can't compress. But if a file pattern is very simple, such as or uniformly bad or uniformly in one color or not, or if it's just complete noise, then that can be compressed or not. And then it goes on to normalization to arrive at the one particular value. Here it's called PCI. If PCI is calculated as 0.55. So if you do that, then what you can get is that for one particular subject, you can compute this wakefulness based PCI, perturbational complexity index, and then that corresponds to, in this particular case, 0.51 for one particular subject under one particular conditions of the TMS stimulation here. And then the other cases, such as non-REM sleep or different non-REM sleep with different strengths of the stimulation. Here, top is 90 volt per meter, and the bottom is a non-REM sleep 160 volt per meter. And if it's weak stimulation, then stimulation remains relatively local and then dies out really very quickly. And that's quantified as this significant activity that is short-lived and relatively uniform. And then that kind of pattern is relatively easy to compress by the zip algorithm. And therefore, PCI index becomes 0.23, much smaller than 0.51. Okay. On the other hand, this strong stimulation, 160 volts per meter, in fact, generates a huge response across all the brain areas. And even if you do that source localization, it can result in this kind of massive response, right? The interesting thing about this zip algorithm or Lempel-Zip complexity is that if it's just bigger response and a more extensive response, it's also easy to compress. And therefore, the PCI value itself becomes small. Compared to this one, the wakeful pattern, intuitively you can feel like, oh, maybe top left is a bit difficult to compress or predict what's going to happen across the time or space. But the right side, this one is more or less easier because it's almost always going up and down, right? So that's the sort of the idea of this PCI complexity index is trying to capture over the time and the space to quantify the complexity of the EEG response triggered by the TMS. And this is a summary of many of the experiments that they have done, reported in Casarotto 2016 paper. Here, first, they report on the healthy subjects results. And the healthy subjects were tested at least 4 times, and then with a different location or different strengths of the stimulus. So here, this is a 1 person tested 4 times or 5 times, and the maximum is the one that they took as the meaningful value, because when it's electrodes were located in a bad way or TMS is oriented in a weird way, it can result in a lower estimate like this way. But as long as we hit on the right location that consciousness locates, then it should be maximally estimatable. So that's the idea. And then basically what you can see is that healthy subjects are in general really high in terms of perturbational complexity index, PCI, right? And then next, when they look at these things, and by the way, it's important to also point out that all of these cases, they report that they are conscious. And they can report it verbally and so on. Even though this experiment didn't show any kind of stimulus or require any motor response, you can imagine that the 15 minutes of the experiment, while you are observing this patient, they are awake, and then when they are randomly asked about wakefulness, they can just report immediately. Now, the next experiment is this situation where the behaviorally unresponsive. For example, non-REM sleep situation, people are presumably not dreaming 50% of the time, and then 4 times of the stimulation and computing of the perturbational complexity index resulting much lower values compared to the wakefulness. And each of the line again, column is different subjects. And then under this situation, of course, people don't report conscious experience at the time of the TMS-EEG. Now, different kind of anesthesia has been tested: mediazolam or xenon or propofol. These are all known not to generate, knocks out consciousness under the certain, dosage. And again, here they also see that people don't report consciousness, and PCI is lower. And some of the drugs are difficult to administer many times. So each subject was tested only 1 time, and but that's still like as a population, it's not like some of the anesthesia doesn't work. It's general across sleep and anesthesia for now. And then interesting 2 cases of the delayed report is that here, after the REM sleep, even though during the REM sleep itself, subjects are not reporting anything, online, if you wake up subject from REM sleep, 90% or more of the time, people do report vivid experience. And the major perturbational complexity index is always high, like here. And the ketamine is another anesthetic drug. And when it's applied with a low dosage, it also induces something similar to dreamlike experience. And here, in this case, people who reported dreaming-like experience because of the ketamine, they also showed higher PCI values. So it seems like even though we cannot confirm consciousness at the time while they are undergoing this, later delayed report can make sure that these are highly reliably distinguishing between the non-conscious versus conscious type of the sleep or anesthesia. And then finally, here they looked at this brain injured patients on the right side. And the brain injured patients, but who have a capability to report conscious experience immediately. And they include the locked-in syndrome patient or subcortical stroke, the stroke that doesn't affect consciousness, or cortical stroke that doesn't affect consciousness, or emergence from the minimally conscious state. So these are the people who still have a lot of problem in moving and also, articulating or talking and reacting, but they are definitely conscious. And all of them have, produced a high PCI with, immediate report of the consciousness. And then this horizontal dotted line, this is a line PCI star, value of like 0.031. This, once you use that kind of threshold, and then look at the maximum that is attained by each of the state, then it turns out that this PCI star is highly reliable to distinguish between conscious states versus non-conscious states. So this is a relatively easy case of the difference between the conscious versus non-conscious, because we dealt with only those people who are either healthy participants on the left side, who can be, who can report, can report the absence of consciousness or consciousness, presence of consciousness afterwards or immediately, or brain injured patients who are highly conscious, and depending on the way to communicate, we can make sure their consciousness relatively, objectively easily. But the power of the PCI comes from this kind of, difficult cases where they can't make a meaningful communication. First, this graph on the left side has been constructed by the cases of immediate report of the healthy subjects or brain injured patients, which is red, or delayed reports of the conscious presence from REM sleep or ketamine, versus immediate report or no report of the consciousness under the anesthesia or deep sleep, non-REM sleep. And then based on this PCI star measure, 0.31, they looked at the correspondence with the brain injured patients whose state is unclear. Here's the result. So according to the clinical criterion of this CRS, coma recovery scale, revised, this is a numerical numbers, coming from multiple testing of the clinicians on each of the patients. And then these minimally conscious state patients who sometimes show evidence of the consciousness or not, this minimally consciousness patients minus and plus is the degree of, this consistency and the complexity of the behaviors. They all, pretty much all, except for 2 patients, have the generated PCI values. That means that, even if they can't communicate or, produce any verbal responses, if they are stimulated directly by brain, and also its response is measured in terms of complexity, they show this, large PCI values. On the other hand, this classically classified behaviorally unresponsive or vegetative state patients, they largely generate a very low PCI values. And many of them, as a maximum, it's almost always 0. That means that, response is triggered, but either very inconsistent or doesn't propagate anywhere. So it results in almost extremely simple, compressible kind of, pattern. And then further, many of them produces much less complexity in terms of the brain response. But some of them do generate, large value of the PCI. And concerningly, it's labeled as, 3 or 4 or 5 very low level of behavioral responsiveness according to clinical criterion. We don't know these, cases are actually conscious or not, but at least, from the evidence of this PCI, it may, imply that these patients are potentially minimally conscious rather than vegetative states. Okay, and the summary of this figure is the table here. So PCI, the max PCI values for minimally conscious state patients are above certain threshold PCI star, in most cases 36 out of 38, and the vegetative state case, it's 9 out of 43, but most of the cases it's 21. And then some of the cases, 13 out of 43 cases, it's exactly 0. So maybe 0 cases is a bit difficult to imagine that anything is going on, but at least some cases may be worth thinking about further revising this behavioral paradigm or examining more of the patient's consciousness in different ways. If the PCI is really valid level of estimate of the consciousness. So in summary, PCI values were lower than PCI star 0.31 in the known states of loss of consciousness: brain injury, vegetative states, or general anesthesia, midazolam, xenon, propofol, and sleep, non-REM sleep. These are all the cases where the PCIs were lower than 0.31. On the other hand, PCI values were higher than PCI star in the known states of consciousness. That means wakefulness, including healthy and brain injury patients that are damaged in terms of minimally conscious states, plus or minus, or locked-in syndrome, or subcortical or cortical strokes, and so on. And then ketamine and the REM sleep generates an experience, so they are also consistent with this idea. And so, in short, TMS-EEG-based paradigm is currently most reliable in discriminating loss of consciousness from presence of consciousness. And the success comes most likely from the fact that it is skipping the sensory and motor areas, and it is probing the base evoked activity rather than spontaneous activity, which can also reflect the connectivity or structural connectivity of the brain rather than ongoing dynamics itself, which is going to be important in the next week. And then most importantly, this TMS-EEG paradigm is likely to reflect integrated information according to the IIT kind of idea. And then if that is correlated with the consciousness or the essence of consciousness, maybe that's the reason why TMS-EEG has been working so well. So now the questions. What about the IIT's predictions on the boundary, the locus of the consciousness, as well as the contents of consciousness? And how can IIT, in principle, explain why different areas of the brain, such as FFA or T8 or MT, can generate different types of the consciousness, and also visual versus auditory consciousness? How can we measure integrated information? We use the proxy of the TMS-EEG this time, but can we ever compute the integrated information? How can we test the IIT properly, more directly? So these are the questions that I'm going to address in week 11 and 12 lectures. So wait for it and see you next week. Bye.